In abstract algebra and formal logic, the distributive property of binary operations generalizes the distributive law from elementary algebra. In propositional logic, distribution refers to two valid rules of replacement. The rules allow one to reformulate conjunctions and disjunctions within logical proofs. For example, in arithmetic, 2 equals plus, but 2 plus. In the left-hand side of the first equation, the 2 multiplies the sum of 1 and 3. On the right-hand side, it multiplies the 1 and the 3 individually, with the products added afterwards. Because these give the same final answer, it is said that multiplication by 2 distributes over addition of 1 and 3. Since one could have put any real numbers in place of 2, 1, and 3 above, and still have obtained a true equation, we say that multiplication of real numbers distributes over addition of real numbers. Definition. Given a set S and 2 binary operators and plus on S, we say that the operation is left distributive over plus if, given any elements x, y, and z of S, is right distributive over plus if, given any elements x, y, and z of S, and is distributive over plus if it is left and right distributive. Notice that when is commutative, the three conditions above are logically equivalent, meaning the operators used for examples in this section are the binary operations of addition of numbers. There is a distinction between left distributivity and right distributivity. In either case, the distributive property can be described in words as to multiply a sum by a factor. Each summand is multiplied by this factor and the resulting products are added. If the operation outside the parentheses is commutative, then left distributivity implies right distributivity and vice versa. One example of an operation that is only right distributive is division, which is not commutative. In this case, left distributivity does not apply. The distributive laws are among the axioms for rings and fields. Examples of structures in which two operations are mutually related to each other by the distributive law are Boolean algebra, such as the algebra of sets or the switching algebra. There are also combinations of operations that are not mutually distributive over each other. For example, addition is not distributive over multiplication. Multiplying sums can be put into words as follows. When a sum is multiplied by a sum, multiply each summand of a sum with each summand of the other sums, and then adding up all of the resulting products. Examples. Real numbers. In the following examples, the use of the distributive law on the set of real numbers is illustrated. When multiplication is mentioned in elementary mathematics, it usually refers to this kind of multiplication. From the point of view of algebra, the real numbers form a field, which ensures the validity of the distributive law. First example. During mental arithmetic, distributivity is often used unconsciously. Thus, to calculate 6/16 in your head, you first multiply 6/10 and 6/6 and add the intermediate results. Written multiplication is also based on the distributive law. Second example. Third example. Here the distributive law was applied twice and it does not matter which bracket is first multiplied out. Fourth example. Here the distributive law is applied the other way around compared to the previous examples. Consider since the factor occurs in all summand, it can be factored out. That is, due to the distributive law one obtains matrices. The distributive law is valid for matrix multiplication. More precisely, for all matrices and matrices, as well as for all matrices and matrices. Because the commutative property does not hold for matrix multiplication, the second law does not follow from the first law. In this case, they are two different laws. Other examples. Multiplication of ordinal numbers, in contrast, is only left distributive, not right distributive. The cross product is left and right distributive over vector addition, though not commutative. The union of sets is distributive over intersection, and intersection is distributive over union. Logical disjunction is distributive over logical conjunction, and conjunction is distributive over disjunction. For real numbers, the maximum operation is distributive over the minimum operation, and vice versa. Max equals min, max, and min equals max, min. For integers, the greatest common divisor is distributive over the least common multiple, and vice versa. GCD equals LCM, GCD, and LCM equals GCD, LCM. For real numbers, addition distributes over the maximum operation, and also over the minimum operation. A plus max equals max and a plus min equals min. Propositional logic. Rule of replacement in standard truth functional propositional logic. Distribution in logical proofs uses two valid rules of replacement to expand individual occurrences of certain logical connectives within some formula, into separate applications of those connectives across subformulas of the given formula. The rules are, and where, also written, is a metalogical symbol representing, can be replaced in a proof with, or, is logically equivalent to. Truth functional connectives. Distributivity is a property of some logical connectives of truth functional propositional logic. The following logical equivalences demonstrate that distributivity is a property of particular connectives. The following are truth functional tautologies. Distribution of conjunction over conjunction, distribution of conjunction over disjunction, distribution of disjunction over conjunction, distribution of disjunction over disjunction, distribution of implication over equivalence, distribution of disjunction over equivalence. Double distribution. Distributivity in rounding. In practice, the distributive property of multiplication over addition may appear to be compromised or lost because of the limitations of arithmetic precision. For example, the identity 1/3 plus 1/3 plus 1/3 equals 3 appears to fail if the addition is conducted in decimal arithmetic. However, if many significant digits are used, the calculation will result in a closer approximation to the correct results. For example, if the arithmetical calculation takes the form 0.33333 plus 0.33333 plus 0.33333 equals 0.999991, this result is a closer approximation than if fewer significant digits had been used. Even when fractional numbers can be represented exactly in arithmetical form, errors will be introduced if those arithmetical values are rounded or truncated. For example, buying 2 books, each priced at £14.99 before a tax of 17.5%, in 2 separate transactions will actually save 1 penny. Over buying them together. £14.99 times 1.175 equals £17.61 to the nearest 1 penny, giving a total expenditure of £35.22, but £29.98 times 1.175 equals £35.23. Methods such as bankers' rounding may help in some cases, as may increasing the precision used, but ultimately some calculation errors are inevitable. Distributivity in rings. Distributivity is most commonly found in rings and distributive lattices. A ring has 2 binary operations, and one of the requirements of a ring is that it must distribute over plus. Most kinds of numbers and matrices form rings. A lattice is another kind of algebraic structure with 2 binary operations, and, if either of these operations distributes over the other, then must also distribute over, and the lattice is called distributive. See also the article on distributivity. Examples 4 and 5 are Boolean algebras, which can be interpreted either as a special kind of ring or a special kind of distributive lattice. Each interpretation is responsible for different distributive laws in the Boolean algebra. Examples 6 and 7 are distributive lattices which are not Boolean algebras. Failure of one of the two distributive laws brings about near rings and near fields instead of rings and division rings respectively. The operations are usually configured to have the near ring or near field distributive on the right but not on the left. Rings and distributive lattices are both special kinds of rings, certain generalizations of rings. Those numbers in example 1 that don't form rings at least form rings. Near rings are a further generalization of rings that are left distributive but not right distributive. Example 2 is a near ring. Generalizations of distributivity. In several mathematical areas, generalized distributivity laws are considered. This may involve the weakening of the above conditions or the extension to infinitary operations. Especially in order theory, one finds numerous important variants of distributivity, some of which include infinitary operations, such as the infinite distributive law, others being defined in the presence of only one binary operation, such as the according definitions and their relations are given in the article Distributivity. This also includes the notion of a completely distributive lattice. In the presence of an ordering relation, one can also weaken the above equalities by replacing equals by either or. Naturally, this will lead to meaningful concepts only in some situations. An application of this principle is the notion of subdistributivity as explained in the article on interval arithmetic. In category theory, if an immonad's on a category C, a distributive law S is a natural transformation lambda S such that is a LAX map of monads SS and is a colax map of monads SS. This is exactly the data needed to define a monad structure on SS. The multiplication map is S mu S2 S lambda S and the unit map is eta S eta. C. Distributive law between monads. A generalized distributive law has also been proposed in the area of information theory. Notions of antidistributivity: the ubiquitous identity that relates inverses to the binary operation in any group, namely -1 equals y minus 1 x minus 1, which is taken as an axiom in the more general context of a semigroup with involution, has sometimes been called an antidistributive property. In the context of an near-ring, which removes the commutativity of the additively written group and assumes only one-sided distributivity, one can speak of distributive elements but also of antidistributive elements. The latter reverse the order of addition, assuming a left near-ring. Then an antidistributive element reverses the order of addition when multiplied to the right. A equals y plus xa. In the study of propositional logic and Boolean algebra, the term antidistributive law is sometimes used to denote the interchange between conjunction and disjunction when implication factors over them. C. These two tautologies are a direct consequence of the duality and De Morgan's laws.